speeches since basically the beginning of February. I've got 25 bookings, and I've spoken to over 1,000 people. And the response is kind of interesting. It used to be pretty hard to talk about climate change because the media and the political forces out there essentially have set things up so climate change is not a socially acceptable topic. If you try it at dinner time, sometimes you may see what it's like. So it takes a little courage to talk about climate change. And this is a picture here at, well, go back, UCSD. And there are, let's try it now. Okay, now it should work. There are roughly 300 kids in the audience there. So the audiences are doing pretty well. Let's just try this a second minute. Okay, that's it now. Climate change was essentially not much on Obama's agenda until the protest organized largely by 350.org in Washington, D.C., when they got about 50,000 kids out there marching. Now, when you get 50,000 kids doing anything, it gets the attention of the politicians. And so this is a protest in front of the White House. There's the White House back there, and here we have a polar bear helping to carry a symbol of the pipeline. It really got their attention, and I think changed the dynamics a lot. A couple weeks ago, you remember Archbishop Desmond Tutu from South Africa? You know, big on the apartheid thing. You know, apartheid was ruining their country, and what they did is they got organized a divestiture campaign where people would essentially sell off their stocks in companies that were involved with the apartheid. The Archbishop is calling for an apartheid-style boycott to essentially get people to divest their fossil fuel stocks. And it seems to be catching on. Here are the people at Harvard a few days ago. The students are having a big sit-in there to try to force the president to actually come up with something extremely concrete to get Harvard to stop doing it. I talked to the chancellor of the University of San Diego, University of California at San Diego, about the same sort of thing. He said he was sympathetic, but it was above his pay grade. So what happens is, you know, that's up to the kids. So we've been trying to get the kids interested in this kind of stuff. The World Bank is starting to pay attention to this stuff. Now, the World Bank has been sort of a villain in this piece for a long time. I remember going about a half dozen years ago to meet with the executive vice president of the World Bank, and her name was Catherine Marshall. And what we were doing is we were reviewing the World Bank's work on sustainability. Essentially, when you go through the World Bank documents, what you find out is they're essentially been pushing coal. So their business is coal. And we talked to them about whether that was in humanity's interest, and they basically said, realize, Tom, that we are a bank. A bank. I said, oh, thank you very much. That helps to explain a lot. So anyway, we basically were very upset with them about them not having really anything to essentially go with sustainability in their documentation. And we embarrassed them with that, and so they fixed the problem up. So now the World Bank is having its president says he wants to lead the climate change challenge. So I think he's for real. I think he wants to do something about it. I think the problem is I'm wrapped up in this thing. I feel like a spider is attacking me here. There we go. Good. The problem is basically that they have given bad advice to China and India for a long period of time. And the Chinese and Indians have paid attention to their advice. So now they know that the advice is bad. I mean, everyone in China knows this is a bad deal they have with coal. So the deal is, what do you do about it? So they're trying to fix that problem. This is a fascinating one here. This is John Kerry in Indonesia, couple months ago. And he's talking about climate change, which is interesting to have the Secretary of State talking about climate change. He and his wife have been big on fighting climate change for years. They invited a group that I belong to, the National Religious Coalition on Creation Care, to have dinner at their home. It was an interesting dinner because there were 3 times as many people serving things as there were people being served. It's kind of a very nice dinner. Anyway, Kerry comes up with this statement that climate change is the world's most fearsome weapon of mass destruction. Now, in this crowd here, you folks know all about weapons of mass destruction because you've been worrying about these things for a long time. But let me review a little bit of that. This is what we think about when we think of weapons of mass destruction. We have the sub-launched missiles where one submarine can take out like 240 cities. You know, there aren't a whole lot more cities than that in the world, are there? That's one sub. And if that doesn't work for you, you can also launch the things from land. And then you have the bat plane to deliver things that get in under the radar. So one time we had about 40,000 nuclear warheads. And the number of warheads you need was always more than you had. So organizations like yours and like some of the churches basically got together and said, this is stupid. And they organized a nuclear freeze to stop the increase in warheads. And then once the freeze caught on, the policy guys in Washington said, no, we should reduce the warheads by 5%. So that number would rattle around for a while, and someone else would say 10%. Let's make it 20. So now I think our numbers are down to something like we've lost about 80% of the warheads, which is good. But we need to push further because we now know that if we do something like, I think in the parlance of nuclear warfare, you call it a sucker punch. It's a first strike where you were to successfully strike, say, the Soviet Union and knocked out the whole culture. What would happen is you win the war, but then you lose because the stuff that goes into the atmosphere, the smoke from the war, we neglected it in our calculations, essentially ruins agriculture for a period of 10 to 20 years. And so what happens is you can't feed people in the world and your society goes down because of your attack. So you lose, they lose. It's a lose-lose proposition. So we fortunately got around that. Today we're focusing on other things as weapons of mass destruction. For example, radiological weapons. Radiological weapons is something where you take a bunch of radioactive stuff and you stick it inside a shell and have some dynamite there, and you set the dynamite off and the stuff spreads out all over the place. Some of you may be familiar with a nuclear power plant that we used to have here called San Onofre. If you had one terrorist organization and they went and attacked the spent fuel pool, I don't mean the reactor itself because that thing isn't cooking anymore, but just attack the spent fuel pool, you would essentially have to evacuate about 50 miles around San Onofre. And you folks would be in that 50-mile radius. My house is right here. I'd be in the radius. And you'd have to evacuate it for a long time. That would wreck the economy of Southern California. If that happened, the economy of California would be wrecked. If the economy of California is wrecked, the economy of the U.S. is wrecked. And probably with all this globalization we have, the economy of the world goes down the tubes. So that's just one, terrorist at San Onofre. We should figure out some way to do better on this stuff. Okay, let's talk a little bit about the mathematics behind climate change. Some people have said, this is a good article in Rolling Stones. Sometimes you get really good stuff out of the Rolling Stones. Some people have said we can heat the planet up to 2 degrees C and it's okay. Other people are saying, baloney, we can't do that because now we know a lot more than when we used to say 2 degrees C. Some people are pushing for 1.5 degrees C. I don't know what the right number is, but let's assume 2 degrees C is the right number. We've already heated things up. We've already heated things up about 0.8 degrees, so we have a little bit more to go. So if we take a look at the carbon And anyway, today we measure everything in gigas because, your computer stuff is giga this, giga that, So you measure in gigatons of carbon. And what this says is we're allowed to have about 500 gigatons of carbon emitted during the next century. And that's okay. That's the number. If we do that, we'll be within this 2-degree number. However, if you look at the resources available, economically recoverable resources in coal, oil, natural gas, what you see is this number here, about 2,700 gigatons, as opposed to, say, 600. So we have at least 4 times the amount of recoverable assets as the ones that we were allowed to do. So this says if you're going to meet this 2-degree challenge, you've got to keep about 80% of that stuff underground. That translates into, I don't know how you folks are used to numbers, but this translates into trillions of dollars, $20 trillion. 20 trillion is a little bit above my pay grade, so I'm not sure of, trillions. But let me try to translate that into something that maybe is meaningful to you. I added up the cost of World War I, World War II, the Korean War, the Vietnam War, the Gulf, whatever they call it, the Afghanistan War, the Iraq War, and all that comes to about $7 trillion. So this is about 3 times the cost of all those wars. Now, what you would say is that, hey, this is big league money. Now, the people that own this money want to keep it. What we're saying is you can't have it. That's why we're having these climate wars. That's why you have this extremely well-funded, extremely well-organized effort to cause people to think that climate change is not a big deal. Now, what I'll try to do is tell you a little bit about what climate change is, and you can decide for yourself whether or not it's a big deal. This is the Arctic sea ice in 1984 in September. This is the Arctic sea ice in 2012. Notice a lot of it's gone. You can now take a ship through the Northwest Passage there, whereas before it was impossible. Now, let's talk about energy for a second here. If sunlight hits clean snow, what happens to the sunlight? Reflects. Okay. Now, if sunlight hits ocean water, what happens to the sunlight? Yeah, it heats the water. So what you're doing is you're making it a lot easier to capture the sunlight than it was before when the snow was there. And so since you're capturing the sunlight much more, I think the numbers are something like, used to reflect 97%, now it reflects like about 3%, something like that. What happens is you're putting a lot of extra heat into the water, and so that makes your global warming problem worse. So there are a couple of fundamental questions. One is there a serious problem? Good question. And the second question is, if there is a serious problem, how can we solve it? So I'll be going, those are the 2 pieces I'll be addressing today. This is a place that I love. It's called the San Luis Reservoir. Some of you may know it. It's up there between San Jose and I-5. It's called the Pacheco Pass. The reason I like it is because many of the world's windsurfing records were set there. Not by me, but I used to go up there and windsurf. So it's a lot of fun to go windsurf up there. This is what it should look like. This is what it looked like a few years ago when I took the picture. The water level is down a good 40 feet, and it's worse today. So we all know California is having a tough time because what happens is the snowpack is not as big as it used to be. Our whole system of plumbing, I think we have the biggest plumbing system on Earth, is based on there being a big snowpack, and that water is supposed to melt, that snow is supposed to melt gradually and basically give us water here in San Diego and other places. What's happening is there's not as much snow, and when it melts much more quickly. So those are the two problems. So we're getting more flooding than we used to. This is a graph here of temperature of the planet, average temperature, going back to the American Civil War. So we're talking Abraham Lincoln kind of time here. And what you notice is the darn temperature, this is where we are today, out here. So what you see is the temperature dances around. There's a lot of bouncing around. Have you ever driven in a car with bad shock absorbers? You know, the Earth is like that. So it's like what we call an underdamped system. The thing dances all over the place. So in order to make any sense out of the data, what you often do is you will take the data and average it over some period of time, like 10 years. And so if you average the data over a 10-year period of time, you can see a lot of that dancing around goes away. And you can see not much is happening here. It's going up a little bit here. This is called World War II and afterwards. And then it's going up here. During World War II, we conducted a giant unplanned experiment. That is, we wanted to win the war. Now, I was in Pittsburgh, Pennsylvania, and as a kid, and as you saw the smoke going up in the air, you cheered because it meant you were winning the war. So when the smoke goes up, what it does is it spreads out, but it also blocks the sunlight. So the sunlight comes and hits the smoke and bounces off the smoke. So what you have there is a cooling agent. But what we found out is a lot of people were dying of chronic respiratory disease, acute respiratory disease, various lung things due to the stuff that's in the smoke. And so we decided that was bad. We cleaned up with our act, with the Clean Air Act. In the process, we saved Los Angeles and a few other places. And so what happened is the Earth could then heat up again. So that's the downside. So here's the Earth heating up here. Now, different people analyze this data differently, and I'll show you one way to analyze it. So there's the same data we talked about a minute ago. So what I'll do is I'll pick a point that I like. That looked like a nice point there. That's one point. Then I'll pick another point that I like. There's 2 points. Are there any math majors in here? Any math? Okay, no math majors. Well, if there were math majors in here, they would know that 2 points determine a straight line. And so we take those 2 points, put a straight line on, and what do we conclude from our straight line? Yeah, it's cooling. So this is what you get from your media people. They say the Earth is cooling. And that's foolishness. That's just called gaming the data. This is an old slide here. It says the 12 hottest years on record were these numbers here. This one doesn't include 2013. I haven't updated it. But if we include 2013, it ties with 2007. So you can say that 13 of the hottest years on record have occurred in the last 16 years. So that clearly says, hey, things are not cooling down. Here's another picture of the ice. This is what the North Pole area looked like in the 50s. The whiter you get, the thicker the ice. The greener or the blue, the thinner. So it looks like that in the 50s. Around now, it looks something like this. And it's projected to look like this in the middle 50s. So you can see much of the north is going to be gone. Now what that does is that changes the whole nature of the heat balance at the North Pole. Now, the same thing isn't happening at the South Pole because the South Pole is on a big rock, okay? And you got 2 miles of ice on a big rock. And so you're not going to get the same rapid kind of response you get there. So what we're getting into is what we call an asymmetrical planet. Big hunks of white stuff on the bottom, not as much white stuff on the top. That completely changes the nature of the climate of the Earth. Now, exactly what that means is a pretty tough thing, but it's not good news. This basically shows that during the next 40 years or so, we will lose about half of the ice in the north area. Okay, let's look at the science behind some of this. I love this picture here. This is a satellite photo of sunset. And notice this thing here. That's our atmosphere. Now, when you look up in the atmosphere, the normal conclusion to come to is the thing is infinite, right? It goes on forever. But from this angle, you can see that it's a real thin thing. In fact, it's thinner than the skin of an apple in relative terms. So what we have is this very small thing that can be affected by things. There's one species that before us that affected the whole atmosphere of the whole planet, and that was called blue-green algae. These little things that they grow in the ocean. Took them about 1.5 billion years, and they gave off a poisonous gas that killed off a lot of the other species there. They call that gas oxygen. So the oxygen that we breathe today comes from the blue-green algae, largely. So we're the second species to affect the planet in a big way. Now, so we can say, well, we're number one, because we're faster than the blue-green algae. We're doing all this stuff in like 100 years, where it took them 1.5 billion years. Now, this is the science behind the greenhouse effect. Now, I wanted to tell you that we spare no expense in making these graphics. This is the sun. This is the solar energy coming down from the sun. Yeah, have you ever parked your car somewhere in the summer and forget to crank the windows down? What happens? What happens? Yeah, it gets hot, yeah. So what's the answer? What do you do? It's different.
Put up sunscreens in the windows.
Okay.
So the sun doesn't come in.
That helps, yeah. You can also crank the windows down. So anyway, what you can do is a scientific experiment here where if you crank the window down a little bit, what happens is you'll get some sort of relationship between the temperature and the window height. So basically, as the window gets higher and higher, it gets hotter and hotter. As you get the window all the way down, what happens is you basically have a fairly cool car. So that's how it works. So the amount of carbon dioxide in the atmosphere is something like the height of our window here. It gives you a crude model of it. Now, some of you may think that this climate change stuff is kind of new. This is the first paper that I know about. That's 1896. It's a big paper. I actually read the darn thing, not in the original language, but in the translation. It was like about 20 pages long. Lots of pencil kind of calculations. And what this guy did, his name was Svante Arrhenius, a very famous guy. He was famous for essentially helping Nobel set up the Nobel Prize. And he later won it himself. So what he said is that if you put more carbon dioxide in the air, it will cause the temperature of the planet to rise. Which he lived in Sweden, and he thought this was a good thing. Well, you know, it gets cold up there. So, but he thought it would take thousands of years. So that's 1896. And his numbers were similar to the numbers we have today, except he's just doing the Earth as an average, whereas today our modelers break the Earth up into small cells. A small cell would be something like smaller than the size of LA County. And then they break the atmosphere up into cells. The thing that determines the size of the cells is essentially the speed of the computers. So they figure it out so that the calculations take about a week or two. And then if they get a faster computer, they just make the cells smaller. So and there are many groups that do that sort of thing, and their calculations, they check them against one another. Some of the interest in carbon dioxide got started with this guy, Charlie Keeling. He worked at Scripps. He is the smartest science guy that I've ever met. The reason I say that is because he talked Scripps into paying him full salary for spending all his time on a beautiful mountain in Hawaii. What a deal. And when he first came out, his data was kind of interesting. It said that the carbon dioxide went up in the wintertime and went down in the summertime, up in the winter, down in the summer. And that's because there's more green stuff on the northern part of the planet than there is in the southern part. And so what we're seeing is the plants are eating carbon dioxide, essentially. But so he didn't get in trouble over that, but he got in trouble over this idea that what this curve is doing what? It's going up. That got him in trouble. So a lot of people said, you know, you're stupid for building your observatory on top of a volcano. Everyone knows that's the wrong place to measure CO2. So what they did is they got 7 sites around the world, you know, North Pole, South Pole, Sweden, Vladivostok, all over the place. And after a few years, they compared the data, and the data was identical. No difference. So he was doing fine. And now I think there's something like 150 sites going the same way. The reason things are going up is because the amount of carbon dioxide that we've been pumping into the air has been increasing significantly since the Civil War, and you can see it went up like that. And it's still going up. So as you put more stuff in there, it basically, some of it stays in the air. Some of it goes in the oceans. This is an interesting shot here. Whenever a big hunk of ice falls off of a glacier, what happens is sometimes the thing will tilt over. So whenever the ice is forming, these lines here were actually horizontal. And so you can see it's like the sort of like the rings in a tree, you know, where you can use that to date the thing. So if you just picture drilling a hole sideways through here, you can get some idea of what these ice cores are like and how they tell the years. This is one of the ice cores here, cover of Science magazine. They've been drilling down to a couple miles deep. Now the problem is you can't go much deeper because there's no ice. I mean, when you get back roughly about 1 million years, you run out of ice. So I'll take you over some of that data. This is the data for the last 800,000 years. This is the carbon dioxide data. Notice here, this is 180 parts per million. The bottom of these curves, these are like 8 ice ages. The bottom of the curve is 180 parts per million, and the top of the curve is 280. So in the last million or so years, it stayed between 180 and 280. Now when it gets up to the top part, that indicates that that's a warm period. When it gets to the bottom part, it indicates it's a cold period. Let's look at the temperature. This shows you the temperature for the last 800,000 years. Here's a peak here. Notice the peak is there. Here's a bottom here, bottom there. There's a pretty darn good correlation between the temperature and the CO2. Sometimes the temperature leads, sometimes the CO2 leads. It sort of depends on what's happening. If you get into a thing where you get like a bunch of volcanoes popping off, that'll cause the CO2 to lead. Now, this basically says that the natural behavior of the planet for about the last million years or so is between 180 and 280. So that's not hard. It's 100 parts per million difference. Now, let's see where we are today. If we look at last year's data, in 2013 we were up to 400 parts per million. That's 100 parts per million more than the most we've seen in 1 million years. Now you say, where are we going? Let me show you. If we continue business as usual for another 40 years or so, what we'll find out is that we'll be at 600 parts per million. That's going to be enough to really screw up the planet. I mean, we already are making significant inroads into the planet, but this is going to be really nasty. Do any of you drink things like Pepsi-Cola or Coca-Cola? Any of those here? None of those? Just a few? Okay, so we got a few. One of those, what's in those bubbles? CO2. Okay, so what happens is the CO2 comes bubbling out and it makes it taste better than it would taste if the thing was flat, right? Okay, now, so what happens, so we're used to the idea that if we have some CO2 in the air, that some of that CO2 is going to make it across the surface of the water into the water. So the CO2 will go into the water, and the more CO2 we have in the air, the more goes into the water, and so the oceans are going to acidify. This is a map, just to give you some idea. This is Australia, here's South America. This is, these colors represent what the pH of the ocean is. Let's see, go back here. What the pH of the ocean is in 1900. So what you see is some dark areas and some lighter areas, but it's basically blue. The red stuff is, these are tropical coral reefs. The purple stuff up here, which is kind of hard to see, are cold temperature reefs. Now I'm going to shrink that down. This is the pH scale. The chemists have this crazy scale where as the thing becomes more acidic, the numbers get smaller. So that's just the way chemistry is. Here's what things look like in the year 2000. You see the dark patches are gone, and here we have some light stuff here, so we're now getting down into here around 8.1. The projections for 2040 are we get a lot of this green stuff. There's no dark stuff, very little dark blue. So we're now down into this area here, 7.9 to 8. In 2060, it's all green and yellow. So that looks like down in here. And by 2085, you have what I would call the Tommy Trojan colors. You know, it's all red and yellow. So what they do is they spend a lot of time with the people at Harvard in the MBA program trying to teach them one question. And that question is, so what? So let's do the so what thing. So what do you care about the pH of the oceans? This is a critter in the ocean. It's called a sea butterfly. Some people call it a pteropod, like, you know, pterodactyl, you know, like the winged dinosaur. Pod means foot, and I'm getting tied up my feet here again. This thing, I'm not used to being lassoed while I'm talking. And pod is like a foot. So it's like a snail that's figured out how to use its foot for wings. This critter is about my thumbnail size, and it's a major component of many food chains in the ocean. There's a lot of stuff that we like depends on eating these pteropods. This is Jane Lubchenco. She's the former administrator of NOAA, National Oceanographic and Atmospheric Administration. I'd like you to hear her comments on this.
Here we see the normal, healthy pteropods swimming through the ocean. This is what it should look like. And now, that is in ocean water.
Don't let your mic and his mic.
Yeah, just turn that one off, please. Okay, well, we...
This increasingly acidic ocean. The shell is completely dissolved.
I'll dub in Jane's piece, okay? What she's basically saying is that there's a pteropod. You saw it swimming. Cute little thing. And if you stick that shell of the pteropod in the water, like they're predicting for the end of the century, that the shell totally dissolves in 45 days. So what does that mean to the pteropod? Does it say, so what? Yeah, it's gone. So the pteropods will go extinct. And so what that means is whatever the food chain is that they're in is going to have a problem if it's a major part of the food chain. So it's not just the pteropod. There are lots of other animals, things in the ocean that are affected. Oysters are affected. What happens is their reproductive system gets messed up. Oops, can we get rid of that hum? Thanks. Their reproductive system gets messed up. Their nervous system gets messed up. Their immune system gets messed up. So it's really a bad news thing for a lot of critters in the ocean. Yeah, if you can just turn that thing off. And,
It is off, yeah.
oh, good. Hide it somewhere.